Thank you.
I had a teacher once in high school where every time someone would sneeze, we'd say "God bless you" in like 14 different languages. That was like her bit. So I mean,
Like-
I have an urge every time to say a different language when someone sneezes.
Interesting. So like, everyone would separately say it in a different language? Interesting. Love that.
She was just a sub. She was a substitute teacher.
Best sub ever. Are you doing the obstacle course?
No, I'm trying to finish score to do it though. I'd love to go watch score and do it.
Does it look tough?
It's just snowing. It's like,
Yeah.
I don't know how I feel about it.
I saw it when I walked in this morning, and they were like playing music in the snow, and it didn't look fun.
That's the most Red Bull thing now. It's like,
Yeah, true.
that is like
I had a nice break between class.
Yeah, just go crush it in like 5 minutes and be done.
yeah.
I leave the bathroom and just come back all stoned.
Yeah. Yeah, the lecture was going slow today after all. All right. Happy Thursday. How's everyone doing? Solid. All right. So we have a big one today. This is one of my favorite topics we're going to cover this entire semester. We're really beginning with the general linear model today. So we're introducing essentially, hopefully we'll make our way all the way to the central limit theorem. We have a lot of intuitive work to get through today. So we're going to spend, the entirety of the class period essentially building up to sort of the grand crescendo of sort of the core idea that we're going to use throughout the semester. We have a lot of work to do that's going to build on top of what we do today. So we're going to spend enough time to truly get the intuition for why we don't fundamentally need to know the underlying distribution of a data set to be able to work with it. And this is not trivial. This is, we use this idea really in every branch of science. Whenever we're trying to know something about a thing that we can't observe directly, we use this idea, what we call the central limit theorem. Just as a bit of background, how many of you have seen the central limit theorem before? Okay, interesting. So this is typically taught in statistics classes, so you've probably seen it before, but you may not have seen kind of the idea in its under the title that it's given. So you will, hopefully some of this is kind of a review. But before we get there, we didn't get through all of our slides from last class, so we're going to start with a refresh of what we did last time, and then we're going to get into the new stuff today. I'm just frankly very excited to walk through these ideas. I think it's one of those things that's underappreciated and incredibly powerful. I'll mention some of these things a little bit later, but we really use the central limit theorem in every branch of science. So what we do in economics, but also when we smash atoms together at the Large Hadron Collider. When we're trying to estimate the weights of subatomic particles, we use this thing we're about to talk about today. So it's just incredibly wide-ranging in its application. Okay, so just as a refresh of what we did last time, we're starting to talk about statistical models. So, how do we go from a data set to something that we can actually work with and make inferences about? we started last class, talking about summary statistics. So it's like we've spent all semester dealing with data sets visually primarily. It's like our human brains are just very good at seeing pictures and interpreting what's going on using pictures. So that's really the place we start. But then if I were to ask you to summarize the price elasticity of demand using a visual, like just visualizing the data, it's not really going to be enough, right? Sometimes we need something more concrete to put into our models. So like you have a demand curve and you need some parameter that determines the elasticity. A picture is not the thing we want. We actually want a number so that we can put it into our equations. So when we're thinking about those kinds of applications, which is something we do all the time in economics, is look for a particular number for the something like the underlying price elasticity of demand. We need something better than a picture. And so we talked about last time measures of the data. So one of the ways we measure data is by looking at the middle point, or the measure of centrality. And so we talked about 3 different alternatives, which you've all worked with before. This was mean, median, and mode, sort of the middle points in a distribution. And then we also talked about variance, standard deviation, and a little bit about range. So we walked through some of the derivation for, like the discovery process, essentially, of why we use standard deviation and not other types of approaches. So you'll remember, we had our core measures of centrality. We had mode, the most common event in our data. We had median, which is really the value we like sort everything in terms of some order, and then we pick the middle ones, just splitting the data into upper and lower halves. And then we have mean, which is the one we like the best for mathematical reasons. It's like sort of the easiest to compute. Median looks pretty simple, but it turns out it's a little more complicated to actually compute, and it doesn't respond as well to sort of standard mathematics. So when we're taking derivatives, for example, not something we'll do in this class, but something that we often do in statistics, the mean is just sort of much easier to work with. And it looks like this, just the weighted average, essentially, of all of our observations. And so we walked through an example with the class ages, and a little tennis example. So you remember we computed the distribution of ages in the class. So this was like the histogram of ages. And we found the measures of centrality for the class's age. And so we had the mode, which turned out to be 20. We had the median, which also turned out to be 20. And then we also had the mean, which was like right on 20. It was like slightly larger than 20. And then we also walked through this little tennis example. And so you remember the setup here, which was you and I don't think like really any of you play tennis. At least that's what you told me last class. Like maybe Corin does, but no one else. But let's say we go out to play some tennis. I tell you exactly the distribution of where I'm going to hit the tennis ball. And then you're trying to pick where on the tennis court to live, to stand. And so this was our measure of centrality. We said maybe a good place to stand would be just right in the middle. It's going to sort of minimize how much running you have to do. So we said, okay, we'll take the mean and stand there. So this was our idea of centrality. Then we also had measures of dispersion, so like how spread out is the data. And in the tennis example, before we talked about actually how we measure this, we thought about how we would wish to measure it. So in the tennis example, we walked through and thought about how far we have to run. So if we're playing this game of tennis, I'm telling you exactly where I'm going to hit the tennis ball. You may be wondering, before I commit to playing tennis with Taylor, how far am I going to have to run on average? So we know where we're standing, right at the mean, and then we want to sort of measure how far we have to run. So one thing we thought about doing was just taking the difference between each tennis ball and the place that we're standing, which tells us sort of the distribution of running. And we plotted a histogram of this, which is essentially just the same histogram as the one above, except now it's centered on 0. This was our demeaning process, like recentering on 0. Then we said, well, this is okay. It tells us, the distribution of how far we have to run, but it sort of treats the two directions of running as different values. So -15 and 15 are different distances. And that was undesirable for a measure of dispersion, in large part because the mean of this is 0. So instead, we proposed taking the absolute value. So we took the absolute value, we called this absolute distance, and then we plotted this. And this turns out to be a little bit better. And then if we took the mean of this thing, we could actually get the exact average distance we would have to run each time we want to hit a tennis ball. So this was the 6.36. So I was like, okay, every time I hit you the tennis ball, you have to run 6.3 feet on average. Very precise number. We know exactly how far we have to run on average. But we said this was not a desirable measure of dispersion because we can't actually take derivatives very easily of this thing. It's not differentiable everywhere. It's not going to matter so much for like the work we do in this class, but to get the tools that we will use in this class, we do have to take derivatives. And because the absolute value function is not differentiable everywhere, this is not a function that we like to use. So instead, we came up with one that was pretty close. So it kind of does the same thing, but it's differentiable. So we can actually take derivatives of this, which means we can do just a ton of stuff with it. So we said this was a nicer one, and we calculated what it actually was. So we squared the difference between court location and the place that we're starting, which gives us this thing, squared distance. And we plotted a histogram. Here we said, turns out the units are just really difficult to interpret. So when we square feet, we're talking in terms of square feet, which, if I were to ask you, what does 100 square feet mean in terms of your running distance? Well, you could answer that, but you have to do a little bit of mental work. It's like, well, if I'm running 100 square feet, that's not sort of units that are sort of interpretable. So I want to I know that 100 square feet corresponds to me running 10 feet. So why don't we just do that work for us? Or like have the math do the work for us instead of having to sort of translate a bunch of math. So instead, we just take, to find the variance, we just find the average of these squared terms. But to find the standard deviation, we're just going to take the square root of the average of the square terms. And this was the standard deviation, which is like our core measure of variability in data, which we'll spend a lot of time with. But here you can see the distance, the variability in the data is very similar in sort of unit terms to our average distance run. So this was sort of the progression we took through measures of dispersion. We said mean deviation wasn't right. Mean absolute deviation was a little bit better, but it's not very nice mathematically. So instead we use variance, which is the average squared deviation. And then from there, to make the units nice, we just take the square root, which then does exactly what we did in the notebook. Okay. In every class, I'm tempted to make a Ryan Gosling joke. So this was sort of our core measures of centrality and variability, or dispersion of the data. But we're after kind of a bigger question, which is what is data? So we walked through some of our definitions, which is, you've seen this in your statistics class. This is, the idea is we have a deck and we can stack it however we like. But the deck itself is a random variable. It's a function that assigns a probability to every possible outcome of a random process. And then the way we stack the deck is our probability mass function or probability density function, depending on whether we're talking about a discrete random variable or a continuous random variable. And so we'll look at, I showed you some pictures a little bit later in the slides. And this is essentially just what goes into the deck, and then we shuffle it. So how the deck is stacked is the probability mass function. And then we said a draw from the deck is what we call an observation, which is the essentially just the card that we drew, the realization of a random variable. And then we said a sample is just all of the realizations we've drawn and we've written down on a piece of paper. This is what we call a sample, and our data is just a sample from a random variable. This is how we think about the data that we have sitting on our computers, just the realization of random variables. And then I asked you if the ages in our survey were random variables or observations, and you said observations. We almost never see random variables directly. We essentially only ever see realization of random variables, with a couple exceptions. Okay. Any questions here? So I showed you a couple examples of random variables. You all said you had seen most of these before. Normal distribution, exponential distribution. We're going to work with both of these today. Chi-square distribution, and then a few others. So typically, we if we know the distribution, well, always if we know the distribution, we can compute all of the things about the distribution that we generally care about. So if I know a distribution, and we're going to talk through some examples in a second, we can compute the mean and standard deviation. And then we can answer a bunch of other types of questions about probabilities with the population. And so to sort of highlight this, I think last time we set up the bet with a rich person, generic rich person. And this is, I think, where we left it off last time. So we introduced this bet with a rich person. We said, okay, we have, with our setup here, we're going to toss a coin. If it comes up heads, you get $10 million. If it comes up tails, you lose $1 million. And we're trying to find some characteristics of this known distribution. I asked this of you last class, right? How many of you said you would take this bet? I think it was no one. So I have a couple other sections of this class, and I had one person say that they would. And their reason, I asked them why. They said, well, if I lose this bet, I'm just going to file bankruptcy. And then, it ruins your credit score forever, but then you don't actually have to pay the $1 million. But then you have a 1/2 chance of actually having $10 million, which is close to enough to retire on. So maybe you all are sort of rethinking your answer. So we actually calculated the expected value here, right? So let's set this up like we did last time. So if we win, we get $10 million. Maybe be thinking about why you're not going to take this bet. Once we calculate this, I'm going to show you that on average, you're going to be much better off with the bet than without the bet. So if you win, you get $10 million. If you lose, you have to pay $1 million, so it's a -1. we have a win probability of 1/2, we have a lose probability of 1/2. And so what we're wondering is, what's sort of the expected value, like the average outcome of this bet? And so the way we set this up, you'll remember, is we multiply the win value times the probability of winning. So how many times are we going to win? Times the payoff in that state of the world, plus the lose value. So how much do we have to pay if we lose? And then the probability of losing. So we just add these two things together and we run this. So here we've calculated what we call the expected value. This is the middle point of the data, or the middle point of the random variable, the probability density function. So someone interpret this. What does this number mean? Like, I said it in one way, in a sort of technical way. Someone just describe what this number means, kind of intuitively. Corin, as always.
It's your expected payoff for a given outcome based on the decision.
Yeah. So it's like, what can I expect kind of on average, right? Our expected value is basically like an average outcome. So, I mean, in some ways, like, this is a theoretical, I mean, it is a theoretical result. We know everything about the distribution, so we can say everything about it. So we have, on average, $4.5 million. So none of you would take the bet. But if I were to give you the bet 1 million times, would you take that? Yes, everyone would take that. This embeds a core idea in essentially everything else we're going to do in this class. That with this bet, a single time, most people won't take it. But if we run it 1 million times, you almost certainly will. In fact, I think everyone would. And the reason you would take it is because there's a lot of variability in the one bet, but there's very little variability in 1 million bets. Because on average, you know you're going to win. So hold that in your brains. So this is one way of calculating the expected value. For time's sake, I'm going to skip the variance and the standard deviation, but you can calculate these things directly. You just need to know a little bit about the distribution. Okay, so instead, what I'm going to do is actually go through and flip a coin a bunch of times. So we know this is a theoretical result, but we can solve known distributions in two ways. And I'm going to ask you to do this on your homework in question 3. You're going to construct for yourself a sample from a known distribution. And then you're going to answer some questions about the sample. So what I'm going to do is, instead of relying on the theoretical result, I'm going to actually calculate the random variable here. And as always, we're going to translate from English into Python using Gemini. So what I've done here is I've constructed a sample of 100,000 coin flips. 100,000 coin flips. And I'm going to pick between the things in this list. So it can either be heads or tails. But instead of listing heads and tails, I'm going to put in the actual values that we see. So if it comes up heads, I get a payoff of $10 million. And if I get tails, I get a payoff of negative $1 million. So we're just going to flip the coin 100,000 times. How long do you think this will take, the computer? I'm going to say less than that. This is a millisecond. Well, it would have been a millisecond. NumPy isn't defined. Okay, so we need to import NumPy. Okay, so millisecond. And then let's just look at our sample. So we flipped the coin 100,000 times. What does that look like? Well, it's a big array. We can turn it into a list just to look at it a little more directly. So we have just a huge list. We have 100,000 observations in our sample. This is our sample. In fact, I'm going to call it sample. This is a sample because what we're doing is randomly drawing from our random variable. We're repeatedly making observations from an underlying random variable. So this is a sample, and this is how we think about samples. And then, like you said before, if I were to give you this bet 100,000 times or 1,000,000 times, like I mentioned, what do you think would happen if we took the mean of our sample? What do you think this number will be? $4.5. Anyone want to say something different than 4.5? I'm going to say it's not 4.5. And you tell me whether it is or not. Is this 4.5? Corin says it's about 4.5. Someone want to make the counter case? Why is this not 4.5? Well, we could just check whether it is 4.5 by a logical check. 4.5, false, false, false. We could continue to randomly sample. We could put these in the same cell so we could take a bunch of samples over and over again. So we're flipping 100,000 coins repeatedly, and it never comes out to be exactly 4.5. So it's always going to come out false. So someone summarize what we're seeing here. We're taking a sample. We know everything about the distribution. We know exactly what the average should be. When we take the sample mean, we're not seeing the average. But we're getting pretty close. If you see 4.49758, would you consider that 4.5? I mean, it's pretty close, right? If we're saying like, what do we expect the average of the bet to be if we run this 100,000 times? I would say like, yeah, basically we're right on the money, just slightly off. It's not exactly, but it's basically right on 4.5. So I want you to hold these two things in tension. First off, it's never exactly equal to the mean, but it's darn close. If we take a larger sample, so let's say instead of 100,000, we take 100 million, how long do you think this is going to run?
Less than a second.
Less than a second? You'd be right. Oh, maybe exactly a second.
You're like a trillion crash.
Have you tried it?
Yep.
Okay. So there's like limited memory in Colab, but this is a little bit closer. Like every time we run this, it's going to be off by just a tiny amount. Like now we're into like 4 decimal places. So a couple of things here, and we're going to come back to this, systematize this, but I want you to be thinking about our results here. First, we know what the average is. We have the theoretical mean. When we take a sample, we get really close, but we're slightly off. And as the sample size gets larger, we actually get closer and closer to the truth. we're going to systematize this in a pretty big idea, and some other things as well. But this is sort of the first picture of sampling. And you will have to do this on your homework, so be thinking about how to do this for yourself. Okay, so this was from last time. We solved the average using both the known distribution, so we know everything about it, so we can solve for the average, and we can solve for the standard deviation, the simulated average. So we can take a sample and then construct the mean. I should also mention we could also construct the standard deviation, so we know the variability of our. Ooh, that took a while. The variability of our data, and you can confirm this with the standard deviation of the known distribution, that they'll be very similar. So I'd say 5.5 would be the standard deviation of the sample, without actually having done the math. Okay, any questions here? I just want to pause on this, because what we just did may feel kind of trivial, but it sort of is our first kind of foray into this really powerful idea with how we can get at answering questions about data that we don't know the distribution for. And we're going to systematize this in a bit. Okay, so in addition to the example we just walked through, we can do other kinds of things if we know the distribution. So if we were to know a distribution, we can answer some other kinds of questions. And some of you, I think most of you will probably have seen these kinds of questions in your stats class. I will ask you if you've seen them before, just so I know your background, sort of familiarity with this kind of thing. Okay, so let's say we know the distribution of bus time arrivals. And let's say I go to the bus stop at a random time. What's the expected amount of time I have to wait for a bus? So we're going to go over to our notebook. I have a distribution here that's sort of better defined. So we're saying we have bus times, we have an exponential distribution. So thinking back to our distribution, the exponential distribution I showed you on that big plot earlier. And we have a mean wait time of 15 minutes, which is kind of bad urbanism. It's like you don't really want to have to wait 15 minutes for a bus. It should be like 5 minutes. But let's say the average wait time is 15. Okay, so we can print out the expected wait time. So we can just find the expected wait time of a distribution. In this case, it's known to us. But let's ask a different question. What's the probability I have to wait more than 20 minutes? How would I go about solving this problem? How many of you have seen a question like this before? Okay. If you haven't, how many of you have seen a picture like this before? We have our exponential distribution, and then we have sort of area under the curve to find probabilities. Raise your hand if you've seen a picture like this before. Okay, nice. So we're going to try to answer this question. I'm giving you the answer in numbers, but we're going to try to answer this question sort of systematically using code. So what's the probability? So if I were to ask you this question, what's the probability we have to wait longer than 20 minutes? How would you go about thinking about a solution process for this question? Like, how would you approach this question? This is a refresh of like statistics concepts, Luke.
Will we use some sort of hypothesis test?
So yeah, maybe we would involve a hypothesis test. I would say that's maybe a sort of more indirect approach. How would we go about computing this thing directly, this pink region? Or is it red? Jury's out. So I mean, one way we could do it is just by integrating under this blue line from 20 minutes to infinity. But that's a bit of work. You all remember your cumulative density function from your stats class? It essentially does the integration for us. The CDF, cumulative density functions, raise your hand if you feel familiar with those things. Okay, almost no one. So I might include some extra description of this in the slides. It may be useful in your homework, but it's certainly useful for some of the things we're going to do in this class. So I'm going to ask you to do a little bit more work on your own. So we're going to use what we call a cumulative density function. And just as a bit of background on this, a cumulative density function, or a CDF, is essentially the integral under the curve from sort of the leftmost, rightmost side to some point in the distribution. So we can specify the area under the curve up to some point on our distribution. So here, we can use a CDF to answer this question. And I'm going to propose the solution concept, and you tell me if this works for you. I'm going to say we find the area under the curve up to 20 minutes. And then we subtract off, we look at the complement of that. You all remember the area under a probability density function is 1. So if we integrate under the entire area, the probabilities of everything in total should not be greater than 1. They should be exactly 1. So we know the area under the entire curve. We can find the red area simply by finding the area under this side of the curve and then subtracting that from 1. And that'll give us the probability of waiting longer than 20 minutes. Any questions here? Okay, so with that in hand, we're going to turn to a notebook. I'm going to do this one for you, but I want you to at least attempt the third question on your own after we've walked through this one. I want you to be able to think in these terms. We're going to use it. So what's the probability that I have to wait more than 20 minutes? So we can find the CDF of this distribution up to 20 minutes. So it's like we're going to integrate under this curve up to 20 minutes. So it's everything that's not in red. So we have our stats package, we have the exponential distribution, and then we're asking it for the CDF. And when we put a number into the CDF, it tells us the area under the curve up to that number. So here, we're asking for the area under the curve up to 20 minutes. So that's this area here. It includes the green area, but it's everything that's not this red area. And then we have this scale parameter, which is the mean of the exponential distribution. So we can determine what the average is for the exponential distribution. And then if we run this, it'll say stats package not found. So we have to rerun these things. All right. So we can run this, which tells us the area under the curve up to 20 minutes. But this is not the answer to our question. The answer to our question is everything that's not this. So all we have to do, we know the area under the PDF, the probability density function, must be equal to 1. So all we have to do is subtract this number from 1. So I'm just going to say 1 minus the area we just computed. When I run this, it gives us 2.6, which is correct. Okay, so we have these tools in hand, and we have our next question. What's the probability my wait will be between 5 minutes and 15 minutes? So we know the picture. We're looking for the area under the curve between these two values. but I'm waiting more than 5 minutes and less than 15 minutes, how would we compute this area? You can see it in the notebook, but someone walk me through the logic.
Subtracting the so that's subtracting their 0 to 15 from 5.
Nice. So we're going to find first the area between, or the area under the curve up to 15 minutes. And then we're going to subtract off the part that comes before 5 minutes. So we find the CDF at 5 minutes, and we subtract that from the CDF at 15 minutes. And that gives us the area under the green region. So we can just compute that directly. So we find the CDF of the exponential distribution at 15 minutes, and then we subtract off the CDF at 5 minutes, and this gives us this number here. Any questions? In your stats class, you may have been asked to do these kinds of things, like finding the areas in the tails of distributions, and then you like have to reference like a z-score. Do you remember that, like z-scores? And then you like take that z-score and you look it up in a table to find the probability. Python does all of that for us. We no longer need a table. You can just run the computation directly. So I'm hoping your life feels way simpler because we have these tools. It feels way simpler to me. I don't keep a z-score table in my office. I mean, it's probably in a textbook somewhere, but I don't use it. Okay, so nice. So we have an answer to these 3 questions. Can I get a temperature check on you all? Are you feeling, if you're feeling overwhelmed by this, 1 finger, 2 fingers for feeling comfortable, but I might need a little more work on this, and 3 if you're just like, this is super easy. Nice, good. All right, so we are in a good place. So this is, with an example using bus times, but I want to do one more example before we turn to the big ideas we're talking about today. This is crucial sort of technical work we have to do before we can truly work with the ideas we're developing today. Let's say we have a distribution of manufacturing errors or manufacturing defects, and let's say we know the distribution. We have a mean of 100 and a standard error of 0.1. This is all in centimeters. We would generally expect this to be normally distributed. There are sort of independent factors which lead to manufacturing defects. Small errors are more common than large errors. So the distribution of errors is going to be clustered around 100. And the 2 tails should have the same size, right? Like large, negative and positive errors should happen with equal likelihood. So we'd expect this to be normally distributed. We have a couple of questions we could ask with this distribution. So how many parts will be shorter than 99 centimeters? So if we were to answer this question, I'm looking for an answer here. How would we find the answer to this question, just using CDFs? What's the probability it'll be less than 99 centimeters? Maybe not a number, but a probability. How would we find that? What if we just plugged in 99 into the CDF of this normal distribution? That'll give us the answer. So here, we're going to set up the manufacturing defects. How many parts will be shorter than 99 centimeters? Well, let's just take the normal distribution, find the CDF, and then look at 99. And we have to be careful here. We have to specify the target length and the standard error. So when we run this, it's basically 0. This is scientific notation for incredibly close to 0. It's 7 after 24 zeros. So it's 0 point, then 24 zeros, and then 7. So that's like 0. Okay, second question for you. How many parts will have errors greater than 1/2 centimeter? How would we use a CDF to find this one? You can look at the code if you like. You can look at the slides to tell me how you would do this in a different way than I've described it in the slides. I'm just looking for someone to answer this. Different words. Gonna leave me on red. Yeah.
Plug it 99.5 into the function and then subtract it from 1.
Okay, so to find it on one side, so we sort of have to think about both sides of the distribution. To find it on one side, we would plug in 99.5 into our CDF to tell us the area under the curve below 99.5.
So yeah, it could be 100.5 on the other side.
Yeah. So yeah, it's basically, in this case, normal distribution is symmetric, so we can just basically multiply that number by 2.
Yeah.
This is one way of approaching it, but let's do it in a different way. So let's find the area under the curve up to 99.5. And that gives us this thing. So again, very small. And then we'll just multiply this by 2. So this is the simple way of calculating it. And these two things correspond. So yeah, very nice. There's a simpler answer than what I've gotten in previous classes. So very nice. Okay, any questions here? I'm dying to start the next slide deck. These are crucial skills. We will use them when we talk about, we're going to use them next week. But just to summarize what we've done here. If we know a distribution, we can do all of these kinds of things, right? We can calculate areas under the curve. We can calculate points in the distribution. I'm going to ask you for the 77th percentile in the data on the homework, and you're going to be able to answer that. If we know the distribution, we can calculate all of these kinds of things. Mean, standard deviation, it's known to us. So if we want to make claims about a population, if we know the distribution, we can do it. And we just did in a bunch of examples. But if we don't know the distribution, we can't do that. What we see is not the distribution, but we see the sample. We see the sample. We see the sample size, so how many observations are there. We see the sample mean, which we constructed a sample mean with our bet with a rich person example, right? We can see the sample and we can see the mean of the sample. And we can compute standard deviation, any sort of statistical concept we like, we can compute it with a sample. But as you saw, the sample mean is not equal to the population mean. So when we can't see the distribution of the underlying random variable, what do we do in that case? This is such an important concept. We use the answer to this question everywhere in science. And to me, it's almost like miraculous that we can even do anything at all with this. With an unknown distribution, can you tell me what the distribution of ages are in the class? Can you tell me what the population mean of the ages in Econ 0150 is? Garrett. So a sample size tells us the size of the sample.
Can't you like assume the distribution at certain sample size to get?
So you could make an assumption about the distribution. So we could say, well, it looks like this sort of peak. Like we have, 18, 19, 20. 20 is the kind of max, and then it looks symmetric. So we could make assumptions about it. But when we bring in assumptions, we are introducing the possibility of being wrong. So it would be better if we didn't have to assume a distribution. But this is assuming a population distribution is something that we do sometimes. Yeah, for sure. So what do we do? Well, the distribution of ages in this class is probably not normal, right? We can have like 40-year-olds taking this class. It's very unlikely. We can't really have like 3-year-olds taking this class. So like the distribution isn't symmetric. We generally have way more 18-year-olds than we have 17-year-olds. And certainly way more than 16-year-olds. Every once in a while we get a 17-year-old in an econ class, someone who like just came out of high school. But I would say a 17-year-old is way less likely than a 23-year-old. So it's not a symmetric distribution. So it's not normal. It's kind of censored at 18 and 22. It's a weird distribution. I don't know what it is. And oh yeah, Luke.
Can it be approximately normal using central limit theorem?
So we're going to talk about the central limit theorem. It turns out we can make big claims about the age distribution of something, the distribution of something related to ages. And it will be related to the central limit theorem. But the underlying random variable itself, I don't know exactly what it is. And the big idea is that I don't need to know. I fundamentally do not need to know what the distribution of the ages is to be able to make claims about it. And that's what we're doing the rest of class today. Okay, big build up. Let's talk about some intuition. Before we get in, are there any questions? I have a bunch of pretty slides for you today. I've spent a long time making them look nice. And we've run through a couple of, we'll run through a couple of simulations here. But this is our big question for the rest of class today. And if we can answer this, we can answer lots of questions about the world without needing to know the underlying distribution. If all we see is the sample, so think back to our example with the coin flips. If all we see is the sample, what can we say about the population? Or another way of saying that, what can we say about the average, the 4.5? If we can answer this question, we're going to be able to make claims about the world. And the general fact, I've said this already in class, but in general, we're never going to be able to see the distribution. We can make assumptions about it, like the ages. It could be a censored normal, so we cut off the tails at 18 and 22. But it'd be better if we didn't have to make assumptions. In general, we only see the sample. So what can we do? So just like we walked through, this was supposed to be the, last slides kind of ran over time. This was supposed to be the first part of class today. Wait times, so if we know everything about the distribution of wait times, we can make all these claims about them. Just like what we did. Area under the curve, we can do it if we know everything about the distribution. But we don't know the parameters, and so what do we do? What we can see is this. This is what we call sampling. We did this with our coin toss example. We're going to take a sample of the underlying distribution. And that's the thing we can see. We can't see the population itself, the mu and the sigma, but we can see these things. We have the sample size, we have the x bar, so the sample mean, and we have the sample standard deviation. And what I'm going to claim to you today is this is all we need. And we're going to develop some intuition for this. What do? We have to do some fancy stuff to be able to work with this, but we can. So I'm going to show you some pictures, and by the end of class today, this will feel intuitive. We have like 20 minutes. We are right on time. All right, so here's the basic setup. We have a population, which I've shown in this picture here. We have our true distribution, which is this blue line. So this is a normal distribution centered around a population mean of 12. So our population mean, the truth, the underlying center point of the random variable itself is 12. Then I'm going to take a sample of 30 observations, and then I'm going to plot the histogram of that. So you can see, I've randomly sampled and plotted the histogram. This is not exactly, it doesn't quite look like the underlying distribution, but it's pretty close. So this is, there's random variability in a sample, and you can see that in this picture. It follows roughly a normal distribution. But the middle point isn't exactly the same as the population estimate, or the population parameter, mu. X bar, the sample mean, is a little bit less. But there are a couple things to notice here, like we did with the coin flip example. X bar is pretty close to the truth, but it's not exactly the truth. 11.5 is close to 12, but it's not exactly 12. So what we want to do, we can see the sample, so we can see the histogram, the green points, and we can see the X bar, that red vertical line. And we want a systematic way of measuring this closeness between X bar and mu. A systematic way of capturing this closeness. And I'm going to show you a sort of an even simpler example before we come back and think about this normal distribution example with wait times. How many of you play Settlers of Catan? I guessed. I thought you might. Anyone else? Anyone who plays both tennis and Settlers? If you don't play Settlers, well, first off, I'm sorry for you. I played a lot of Settlers in high school and some in college. I'm a kind of competitive person, and so when I played with my friends, it led to relationship tension. So I ended up stopping Settlers. I would get so into the game. But in Settlers, you don't have to know how to play Settlers to understand this example. When you roll one die, there's a uniform distribution of die rolls. So if I roll one die, it's equally likely that I get a 1, a 2, a 3, a 4, 5, or 6, right? Each one of the 6 sides can come up equally likely. But think about what happens when we roll 2 dice. If I were to ask you, is a 2 less likely or more likely than a 7? What would you say? Which is more likely, 2 or a 7? Yeah.
7.
And why is it a 7?
More opportunities to get a 7.
Nice. Remind me of your name, I'm sorry. We have 2 Lukes, love it. So Luke is saying 7 is more likely because there are more chances that the 2 dice sort of end up with the sum equaling 7. With a 2, there's only one way it can happen. If you roll 2 dice, it has to be exactly that one dice shows 1 and the other shows 1. Only one possibility. But there are, let's see, 6 ways you can get a 7. You can get a 1 and a 6. You can get a 2 and a 5. You can get a 3 and a 3. Sorry, 3 and a 4, and so on. There are 6 ways of getting a 7. So a 7 is 6 times more likely than a 2. So we have this underlying distribution, which is a uniform, but if we take sort of the sum, or we could construct the average, it's going to be centered, it's going to have a different shape to it. And I'm going to show you exactly what that shape is. So here, I'm going to take a bunch of samples. So instead of just rolling 1 die, I'm going to roll 2 and then take the average. So you can see a couple of things here. First, we have variability in our X bar. So we have 2 dies, and on the horizontal axis, I have the die value. And so we can see there's variability in the sample mean. And you can see the 2 die rolls. So we get a bunch of variability. And this is what the distribution of die rolls looks like when we have 2. This is the distribution of die rolls if we have a sample population of sample size of 1. This is just 1 die, and we just take the average of 1, which is just the die roll itself. But if we take the mean of 2 dice, it looks like this. So this is what Luke was saying. When you roll 2 dice, the middle point is going to be much more likely than an extreme value. So this is the same as saying that 2 is much less likely than 7. And I want you to think about why this is true. This is not trivial. We get this sort of squishing of the distribution towards the middle. We took a uniform distribution, and when we took the average of 2 realizations of the uniform distribution, just rolling 2 dice, it looks sort of pushed towards the middle. We're going to leverage this idea into one of the biggest ideas in modern science. Okay, so this is the 2 die rolls. What if we plot a third one? So instead of taking 2, we take 30 die rolls and take the average of those. It's really difficult to get very extreme outcomes. If you want a 1, you have to get 30 ones. That's the only way you can get a 1 with a sample size of 30. You need each one of them to be exactly 1. And how likely is that? I mean, it's basically impossible. It's like 1/6 raised to the 30th power. Very unlikely. And you can see that in the distribution here. And if we continue this process, we get closer and closer to the middle point. There's less variation as we increase the sample size. Does this red line look familiar? Anyone recognize this? What does it look like? Normal distribution. So we're going to come back to this. But I just want you to notice how weird this is. Weird in a certain kind of way. That when we take repeated samples, when our sample size gets larger, the distribution of the sample mean, it's like X bar, gets closer and closer to a normal distribution. Okay, I think we're right on time. Stay with me. We have 10 more minutes. And I'm going to try to introduce one of the biggest ideas in that short amount of time. So this is the idea with something pretty simple, just rolling dice. And it's weird. It's like the larger the sample size gets, the closer it is to the truth, and the closer it is to a normal distribution. Like this, when we average 2, it doesn't look normal. But when we start averaging larger sample sizes, it gets closer and closer to normal. Okay, so let's go back to our example using wait times. So we're going to do the same thing with wait times. So if you're waiting for your food at a restaurant, we have, let's say this is some distribution. Maybe it looks normal, but we don't know necessarily what it is. So here I've taken 5 samples with a sample size of 30. Each one of these samples, you can see the distribution, and I've plotted the sample means. Each one of them gives us a separate estimate or a separate X bar of the wait times. And again, just like we did with die rolls, we have this variability in the underlying, in the sample mean. So each one of these samples has a slightly different sample mean. We even saw this with 100 million observations. It was like there was variability in the sample mean, even at 100 million. It will, it's sort of always there. So again, we're going to plot these sample means. I'm going to take 500 of them instead of 5, and we're going to plot the sample means, not the underlying distribution. This is what we call sampling error. So we have sort of, each time we take a sample, it's like slightly different, and it's not exactly ever the population. And here what I've done is plot the sample means with a sample size of 30. This is 500 samples, each with a sample size of 30. So the number of draws we've taken is 30 times 500. And what you'll notice is that this is a tighter distribution than the original distribution of wait times. So in orange here, I've just plotted out the original distribution of wait times. So these are the same numbers. It's just in blue, I've shown you the sample means of each one of the 500 samples. And in orange, I'm showing you the underlying distribution of each realization. So just like with die rolls, when we take a sample mean, we take repeated samples and then we take the mean, that distribution is much tighter than the original distribution. Same intuition, 2 is much less likely than a 7. And you can see here, no matter what the underlying distribution is, the underlying distribution may be normal, but certainly the sample means look pretty normal. If we take a larger sample, I'm doing exactly what I told you not to do, which is plot histograms on top of each other. I think this case may be one place where it's maybe useful. You tell me if you don't like this picture. You don't. Shoot. So we have sample means, so we've gone from 30 in blue, and maybe more contrast would be nicer, to a sample size of 60. So we've doubled the sample size, and we've shrunk the variability. You can see the distribution is tighter, and it's centered on the truth. Remember what the truth is. It's exactly at 12. As we increase the sample size, the variability gets closer and closer, gets smaller and smaller, and the variability becomes centered on the truth. If we increase the sample size to 1,000, okay, here's your contrast. This may be a little bit better. We've increased the sample size, and the variability has gone way down, sort of dramatically. This also looks like a normal distribution. Red on top of red is maybe also bad practice. We have an underlying normal distribution which matches very closely this sample size, this sample mean distribution. Okay. I've included an emoji because this is one of my favorite ideas. The sample mean, X bar, follows a normal distribution around the truth. So we know that the distribution of X bar follows a normal distribution, and that normal distribution is centered on the underlying population parameter. So if we take larger samples, they're going to be centered on the truth with less and less variability in the sample mean. Not the observations themselves, but the sample mean. And then we have this fancy thing we'll come to next class with the actual distribution. But you can see the second component in the normal distribution is the original variability divided by the sample size. So as we increase the sample size, the variability gets smaller. Okay, and this doesn't just work with uniform distributions or normal distributions of underlying data. We don't need to know what the underlying distribution is for this fact to be true. What I'm showing you here is a chi-square distribution. So this is the original distribution. When we take a sample size of 5, it gets a little bit closer to a normal distribution centered on the truth. But as we increase the sample size, it gets closer and closer to a normal distribution. Once we hit 30, we generally think it's pretty close to normal. And then you can see the truth is right here. And a sample size of 1,000 gives us not much variability around the truth. So even though we take sample means, and each mean has some slight sampling error, it gets really close to the truth. And now we know what the distribution is of x bar. We know that x bar follows a normal distribution. So even though we may not know what the underlying distribution is, we do know the distribution of x bar. If your mind is not blown, I don't think you've been paying attention. This is the central limit theorem. Tells us the distribution of sample means. Basically, it approximates a normal distribution as the sample size increases. And then generally, like we say, over 30, if your sample size is over 30, you're essentially going to follow a normal distribution. And it doesn't matter what the underlying distribution of the data is. And this is why I told you at the beginning of class, we don't need to know the underlying distribution of ages to be able to say something about the average age. Because we know the distribution of the sample means. Okay, so the sample means cluster around the truth. We have a standard error that's this thing here. It's the true variability, the standard deviation in the truth, divided by the square root of n. So the larger the sample size, the smaller the variability in your sample mean. And then we get this normal shape. So the normal shape is actually going to matter when we start talking about confidence intervals. And it turns out that's really nice. We can make claims about how confident we are because we know this is a normal distribution. And then what this means is we can make predictions about the behavior of x bar. So we know how it's going to vary around the truth. And the key point here is it doesn't matter what the underlying distribution is. All right, I should have included another emoji here. Any questions at this point? I've been kind of talking at you a lot today. Does this work? So take a look at your homework. You're going to work with some of these ideas of sampling in your homework. In question 3, I'm actually directly asking you to sample from a random, just a normal distribution. So with your code, you're actually going to construct your own sample and then talk about the sample. Very similar to what we did in class. Next class, we're going to talk about confidence intervals after our regularly scheduled short mini exam. So stop by office hours. I have office hours directly after class, so feel free to stick around. I just want to convey this idea to you. It's pretty powerful that we don't need to know the underlying distribution, and we can still say stuff. Spent half an hour saying that with pictures. All right, see you on Tuesday. Have a nice weekend.